Hello everyone, my name is Dr. Vile and welcome to my A-Level Chemistry YouTube channel. This is all about getting you ready for your A-Level Chemistry exams. This video is going to focus on a kinetics topic called the Boltzmann distribution, which is all about how temperature and temperature and the use of a catalyst can influence the rate of a chemical reaction. So if you like this video, remember to like, subscribe, keep checking back for more content. Okay, so we're going to be looking at the Boltzmann distribution here. Now, the Boltzmann distribution is a graph. On the x-axis, you've got the energy of the particles, so how much energy they have. And then on the y-axis, you've got the number of molecules that have a specific energy. So for instance, let's just make up some numbers. Just say I wanted to know what the energy was 8. And you wanted to know the number of molecules that had an energy of 8. You would just read up to the line. And you could read off here and you might say that there's 5,000. These are just silly made up numbers, but what this enables you to do is to work out how many molecules have a given energy. And when you have a Boltzmann distribution like this, it looks like a normal distribution curve if you're doing any kind of maths alongside this, where the kind of curve starts at the 0, 0 axis, nice smooth curve up to here, and then it just drops back down again, and it never quite touches the x-axis. That's important. And then the peak of your curve is the most probable energy, because that's where you've got the highest number of molecules at that point. So the peak is the most probable energy. And then what we also do on a Boltzmann distribution is label where the activation energy is. So the activation energy is the minimum amount of energy that's required for a chemical reaction. And therefore anything to the right of the activation energy can react, and anything to the left of the activation energy can't react. And the area under the curve is the total number of molecules. So all of these, if we just shade them in green, all of these molecules here don't have enough energy to react. And all of the molecules that are in grey do have enough energy to react. So a couple of points about the Boltzmann distribution curve. We've just said most of them, but the distribution always goes through the origin. What that means, it starts at the 0, 0 stage. It always starts at 0, 0. When the curve comes back down, it always approaches the x-axis but never touches it. That's important if you're sketching it. Make sure it doesn't touch the x-axis again. The peak represents the most probable energy, and the area under the curve represents the total number of particles. And EA, which was this that vertical line, represents the activation energy, the minimum energy needed for the reaction. And then the shaded portion, the bit in grey, represents the number of particles with sufficient energy to react. And what you need to be able to do is to show how changing temperature changes the Boltzmann distribution curve, and also what happens when you add a catalyst as well. Those are the two things you need to be able to do. Let's start off by looking at temperature. The line labelled T1 is your original Boltzmann distribution, before you change anything. And then T2 is where you raise the temperature. Okay, so T2 is the higher temperature. Notice that the curve is flatter for T2 when you increase the temperature, and that the peak of the curve is further to the right, which means it occurs at a higher energy. So when you increase the temperature, the most probable energy shifts to a higher amount of energy. Okay, and then the curve starts to come back down again, but it comes down less steeply than it did before. And now the activation energy still hasn't changed, it's this line here, but can you see that we've now got this lighter grey shaded area as well as the dark grey shaded area, which means there are now more particles with energy equal to or greater than the activation energy. So what have I written here? There are more particles that have energy greater than the activation energy. The most probable energy is higher, and there are fewer particles with a lower energy. So this white shaded section here is smaller than it was before when we're dealing with T2. Okay, so increasing the temperature, the activation energy stays exactly where it is, but the curve becomes flatter, and therefore this shaded area becomes bigger. All right. And if we add a catalyst, the curve doesn't change at all. However, the position of the activation energy shifts to a lower energy. So now the shaded area is bigger again. So we have more particles with energy equal to or greater than the activation energy. So a catalyst lowers the activation energy. It doesn't change the Boltzmann distribution, but what it does is it moves the activation energy to a lower energy. So more molecules have energy greater than or equal to the activation energy. So you need to be able to draw a Boltzmann distribution curve, give a very brief explanation as to what it is, and then show how it changes for temperature and how the activation energy changes for when you add a catalyst. Okay. Thank you for watching the video. If you found it helpful, remember to like, subscribe, and keep checking back for more content. See you next time.